And so question 9, worth 15 marks, so much more involved. Part A, show that sine x plus cosine x all squared is equal to 1 plus sine 2x. So I'm going to start on my left-hand side. I think it's going to be easier to expand those brackets. And because it's a show that question, I'm going to take this nice and slowly. So I have sine squared x plus sine x cosine x plus sine x cosine x plus cosine squared x, which is sine squared x plus cosine squared x plus 2 sine x cosine x, and then sine squared plus cosine squared is 1, Pythagorean identity. 2 sine x cosine x is sine 2x. And so I've shown what I needed to do as required, nice and straightforward. Part B is a bit more involved. Show that sec 2x plus tan 2x is equal to that whole fraction. I always traditionally find it easier to combine separate terms into one big lump, so I'm going to start on my left-hand side, which is sec 2x 1 over cosine 2x plus tan 2x sine 2x over cosine 2x, which makes my life a lot easier, because that's 1 plus sine 2x all over cosine 2x. And I noticed that 1 plus sine 2x is what I was finding in my first part, and that's probably highly useful to me. So 1 plus sine 2x is sine x plus cosine x all squared. And I'm going to rewrite cosine 2x. And because I note that my denominator has cosine x minus sine x, I'm going to rewrite cosine 2x in terms of both cosine and sine. So cosine squared x minus sine squared x, which is the difference of two squares. So I have sine x plus cosine x all squared divided by sine x plus cosine x times cosine x minus sine x. I can cancel one of my sine x plus cosine x's to get cosine x plus sine x divided by cosine x minus sine x, which is what they wanted, and so I'm sorted. Part C says hence or otherwise, so I know immediately I'm going to be using those results, and indeed I do. I have the integral between 0 and pi on 6 of sec 2x plus tan 2x, which I've just shown is equal to cosine x plus sine x over cosine x minus sine x dx. Now that's not a standard integral I know how to evaluate. However, I note that if I look at my denominator, it's in a very similar form to my numerator, and so it's quite likely, I think, that if I differentiate one, I'm going to get a form of the other. So I choose u equals cosine x minus sine x as a substitution, and so du by dx is equal to minus sine x, when I differentiate cosine x, and then minus cosine x, because when I differentiate sine x, I get cosine x. And so dx is equal to minus du over cosine x plus sine x, which would appear to be very useful, because that's my numerator. So I have the integral between x is pi on 6 and x is 0. It's important I remind myself of that. It's not what u is going to be equal to. Then I have cosine x plus sine x over what I've called u, cosine x minus sine x, times minus du over cosine x plus sine x. And so my numerator and my denominator cancel, and I get minus the integral between x is pi on 6 and x is 0 of 1 over u du, which is minus ln u is my integral of 1 over u, so ln cosine x minus sine x between pi on 6 and 0. So that's minus, and then I have ln cosine pi on 6 minus sine pi on 6, these are values you should know, minus ln cosine 0 minus sine 0, and equally those are values you should know. So I have minus, and then ln, and I know that cosine pi on 6 is root 3 over 2, and sine pi on 6 is a half, pi on 6 being just 30 degrees, and then I have minus and minus plus ln cosine 0 is 1, sine 0 is 0, so ln 1. And I know that ln 1 is just equal to 0. So I therefore have minus ln root 3 minus 1 all over 2, or using the idea that a ln b is equal to ln b to the power of a, I just have ln of 2 over root 3 minus 1. I'm not done because I need it in the form ln a plus root b, so I need to multiply by root 3 plus 1 to rationalise my denominator. And so I get ln, and then I've got 2 root 3 plus 2 over, and then I have 3 minus root 3 plus root 3, they're gone, so 3 and minus 1, so all over 2, which is ln root 3 plus 1, which is the form they wanted for my work. 15 marks, sorted.